Okay, thank you everyone for coming. So this is the Altair Aerospace Coffee Break series, which is now Siemens, so hence the new format for the presentation. And without further ado, we will jump right in. If you have any questions, please put them in the chat, and we'll get to them when I'm done going through the slides, and I'll try to address them in the order that they come. Okay, so anyway, this presentation is going to be a combination presenting bird strike simulation setup and how you can integrate AI to make some of the bird ingestion analysis easier. This is a presentation that I actually gave at the AIAA SciTech conference like 2 weeks ago. So it's called Reduced Order Model, AI Inference of Critical Bird Ingestion Parameters. So here's the agenda for today. First, we had to spend a lot of time in background. What is bird ingestion? What is Radios? What is ROM AI? Then we'll talk about the critical ingestion parameters and then the different workflows with and without AI. Then we'll go through the model setups and the results. So first is the background. Effects of bird ingestion. So there's two types of flows. I'll show you on the next slide. If the bird enters a turbine engine during flight and goes either into the combustion flow or causes some other event, the results can be pretty bad. So this is what happens. This video shows what happens if a bird could cause a blade separation. Yep, pretty catastrophic. So this is an important event that all turbine engine designers have to plan for and design for. However, because physical testing, as you can see, is very expensive and time consuming, now simulation software is widely used. And Radios and ROM AI are some products that can be used for this. This is just some more background. If the bird, and so this is a cross-section, a very simplified cross-section of a turbine engine. The bird can enter when it hits the blades, it can go through the bypass flow, which is these blue arrows, which is harmless, or if it goes through the next stage of turbine blades and into the combustion chamber, that can cause performance issues and maybe other things, other worse things. So basically, we need to determine, how much of the bird is going to be ingested into the engine in the worst case scenario. And in order to do that, there's people used to do some physical testing. This is back in 2002. This is a high-speed camera showing. You can actually see the bird was actually comes out only for a few frames right there, and you can see all the red dust. That's what was the bird. Here's another view. Not much left. So this is, again, expensive and time consuming. So that's why the industry went more towards simulation. So real quick, what is Radios? For those that don't know or don't use it, it's a highly nonlinear explicit solver that was commercially introduced in 1986. It's comprehensive, accurate, and scalable for highly nonlinear analysis like ballistics and explosions like these animations are showing here. That can do even more than that. It can be used for bird strike. Like here's a rendered animation for a model similar to what I'm going to show you later. So this is we have a bird that's modeled as a bunch of particles hitting the blade, and the blade separates and the particles bounce around. So the benefit of using simulation is that you can get results in hours or days, depending on your model size. But the question for this presentation is, can we make it faster and cheaper? Even more so. So next we'll talk about what is ROM AI. ROM AI is an AI-powered technology that creates a reduced ordered model from complex 3D simulation or test data. So basically, it takes the full order model would be the Radio simulation, And the reduced order model basically breaks down the radio simulation into a bunch of parameters and a single output. And then if you feed it multiple simulations with different parameters and different outputs, it starts to create a relationship between the inputs and the outputs. And this changes it effectively into a polynomial. It makes system level simulations much faster and uses the results of the simulations to make a 1D system level study. So for this presentation, we're going to talk a lot about the critical ingestion parameters, which comes from the FAA. And these critical ingestion parameters are bird speed, which basically means the speed of the bird impacting the blades, the critical target location, which effectively is the radius of the bird from the center line of the turbine, and the first stage rotor speed, or the rotational velocity of these blades, and finally the bird weight. So the current workflow to find the worst case scenario for bird ingestion is effectively just guess and check. You create a couple radios runs with different parameters that people are chosen either with engineering judgment or arbitrarily, and then you look at the results for bird ingestion. How many particles go into the engine core or the combustion flow, and then you kind of guess and check from there until you specify down on the worst case scenario. So in this case, there's a lot of repetition, a lot of guessing and checking, and you can end up running a lot more simulations than you may need to, which can be time consuming and expensive. The proposed workflow with ROM AI is to train the ROM AI model with a handful of simulations, and then the model will tell you the predicted worst ingestion and which parameters will result in that ingestion. And then all you have to do is run a single simulation more to confirm a ROM AI prediction. So now we'll talk about the Radios and ROM AI model details. The Radios model that we're showing here is a publicly available engine model. It's just a simplified turbine engine with some surrounding supporting structure. This is something that I can give to anyone that asks. I think it might be available even online already. The assembly is modeled on Radios and uses over 1 million elements with elastoplastic properties. We have a rotational imposed rotational velocity on the turbine blades shown in this teal arrow, and then we have some fixed constraints on the ends of the supporting structure shown in orange. Next is the engine core. So on the left is this cross section here. The highlighted area is the engine core. This is where we're concerned where the bird particles end up. This is where the combustion flow goes. And then that front facing access to the engine core is this gold disc here that you can see. So that's the only way to get into the engine core. And just for simplicity's sake, we modeled the engine core as empty. If you're more familiar with turbine engines, you know that this is full of lots of other components and parts. But just for the sake of the simulation, we emptied it out. And the core goal of this simulation was to determine how much of the impacting bird enters the engine core. So now we'll talk about the bird. The bird is modeled using SPH elements, or spherical particle hydrodynamic particles in Radios. We used 22,000 particles in total. The mass of the bird was evenly distributed to each particle, and the particles were assigned fluid material properties that have both adhesion or attraction and repulsion forces between each particle. So basically, the particles kind of try to hold their shape until some other force acts on them. And this is where the results come in. The bird particle locations is what we're concerned with. You can see here in the top picture, this is the cross section of all the particles at the end of the simulation. You can see that most of them are going through the bypass flow in the outer diameter here. But in the bottom one, we just turned the engine core transparent there, and you can see all the particles that are inside the engine core. So what we're looking for here is how many particles are in the engine core versus how many particles are not. And then we're calling that, this is our target output variable. We're calling that the ingestion ratio. So that's the particles in the core divided by the particles in the core and the bypass. And the reason we're not using the total particles is because you can see here in the top picture, just because of the way these generic blades are modeled, you have some reflection or bounce back of some of the particles, which is not really realistic for multiple reasons. So we're just ignoring those particles that are basically we're bouncing off the blades. So that's why we're only considering the particles in the core and bypass. And here's the ROM AI model summary. We varied the bird distance from the center of the turbine, center line to center line, from 8 to 17, bird impact velocity from 4 to 150 miles per hour, the turbine rotational velocity from 1,000 to 6,000 RPM, and the bird weight was 1, 2, or 3. We used HyperStudy to generate 100 combinations of parameters. In this case, we used 80 combinations to train the AI model, and then the remaining 20 were used to test the AI model. These parameter combinations were not selected by hand. Instead, we used, in HyperStudy, we used the modified extensible lattice sequence, or it's called MELS. And that looks like this. So with the truly random distribution of the parameters, you'd end up with clumps and gaps and things like this, and you might not cover the full range. The MELS distribution is quasi-random. It equally distributes the points while minimizing clumps and empty spaces. And it affirms that the full range of each parameter is used. So with the AI model, this is the basically this shows the error on the model with the model prediction. So the blue curve is the model, the ROM AI prediction. On the y-axis is the error. So you can see we started with almost 50% error or 45% error. And then each epoch or iteration of the model is how it starts improving itself. So you can see after 100 epochs on the training data set, we got it down to, you can see that's like less than 1%. And then finally we inputted, and then we compared the model to we tested it on the test data set and found that the error was less, again, it's like 0.1%. So very good. And if people have more questions on this, we can talk more about this, but I don't want to spend too much time unless people are interested. Okay, so now we'll work on the results. So the high level value is that the correlation is very, very high, very good. The R-squared value was above 99%, which is excellent. You can see here this curve. On the x-axis, we have the Radios ingestion ratio, or the true value. And on the y-axis is the predicted ingestion ratio by ROM AI. And then you can see here the blue dots are the training data set, or the data set that was used to train the AI model. And the test data set was not included during the training, but then used to check and see how close the model was. And you can see that we have excellent correlation. And the next best benefit is that we used 80 simulations, and we got above 99% correlation, or R-squared value. But you can actually get above 90% correlation using just 30, which saves much more time. So what's the takeaway? What's the so what? Without ROM AI, you've got to use hundreds of simulations to identify the worst case parameter combination for bird ingestion. With ROM AI, only 30 simulations are required to train the AI model. And then once you have that model trained up, predictions on the future parameter combinations on the same model or a very similar model can be made in seconds, as opposed to running a simulation for hours or days. This reduces the cost of core hours and engineering man hours and improves your time to market. Additionally, if you do make a design change, you can pick up the AI training pretty much where you left off, and then it'll be, it's much quicker to train an existing model, to update an existing model than to train a new one. So I want to really quick address this model, the limitations of this model. This ROM AI is model specific, which means that if you change the model, you have to update your AI model. And in this case, for the Radios model, we did not model the airflow or gravity. And also, we did not consider impact of the bird on the nose cone. We only considered where the bird would impact the blades first instead of the nose cone. We also only modeled a single bird. We could have done more. And we did not consider any blade damage or separation. And finally, the turbine is stationary and the bird is hitting the turbine, which is, again, not realistic. Normally, it would be the turbine would have a lot more inertia. So introducing any data outside of this model, outside of these model assumptions, would require training a new ROM AI model. And real quick, I want to give a shout out to Nathan Grathwall, who worked on the ROM AI model and submitted the paper for SciTech conference. And then Matisse Loverini from the Radios team in France, who created the original bird strike model that we used. And that is it for now. So let me see. If you guys have any questions, please put them in the chat. And I'm happy to spend the remaining 9 minutes addressing any questions. Let's see if I can open the chat. Okay. I don't see any questions now, but yeah, if you have any, please put them in. And yeah, I have some other backup slides I can show if anyone's interested. All right, the link to the model. I don't know if the model is shared online already. I can, I'll check. No, I think I'm still sharing. Yeah, let me see if it's PowerPoint. Let me see if I can find it. I'll put it in the chat if I can find it. Let's see here. Okay. So I've got one. We already have an example of a bird strike hitting a wing that's already available. I don't know if we have this one posted online yet. I gotta work on that. But for now, if you're just interested in the bird, it's a very similar simulation. It just uses a wing edge instead of the engine. So here is that link. That's publicly available right now. It's already uploaded. Okay, and I see a question from Jim. How much more involved would the analysis be of the bird hitting the nose cone? Yeah, so the only reason we did not model a bird hitting the nose cone is because then we would have to, it was just to make my life easier. We would have had to move the bird in 2 dimensions and then run the simulation longer. So you can see here, if we move this bird down like this, if we move it only in Z, I think it's the Z direction, it would kind of end up like this, which you can't do. So then you have to move it backwards and run it for a longer time, which it would have been a significant increase in runtime, and which we didn't want to deal with. So we just made everything, between the edge of the nose cone and the edge of the inside diameter of the turbine. Does that make sense? It was just to make our jobs easier. Yeah, and in this case, I can't remember if the nose cone was actually rotating or not. I think only the blades were rotating. Let's see if you can tell in this animation. Oh, in this animation, we don't even have the nose cone, but yeah, I think in this case, the nose cone was not rotating, but that's something that we can absolutely incorporate. Yeah. Yeah, that would not be hard to do. You need to include it in the imposed velocity set. Yeah, that's a good question. So I see Tozer I'm not sure if I'm pronouncing your name right, but Tozer Gavin was asking if more input parameters will require more models. That is a good question. Yeah, I'm not sure. I would imagine it would. You know, the more complex, your parameter distribution is, the more models you need to accurately train it. But I'm not sure. I would assume yes, but I'm not sure. I'm not sure. Okay, good. Okay, I'm seeing lots of questions now. Nice. Okay, from Sean, how easy is it to vary the properties of the bird through the SPH? Oh, that is not easy. So if you want to, basically, it becomes a whole other simulation or modeling process. If you want to model a non-homogeneous bird, so bone, feathers, and all that stuff, effectively, if you want modeling by it is very complicated. For anyone who was modeling crash dummies for automotive or aerospace for occupant safety, those crash dummy models have millions and millions of elements and all sorts of joints and things, and yeah, it gets pretty complicated, especially when you start incorporating bone and soft tissue and things like that. Yeah, so it would be if you just want to make different regions of if you want to keep everything SPH elements and then have different um, attraction and repulsion forces between the elements, that's actually not that hard to do. You just need to put different properties. So, for example, if you wanted to, let's see if we can go to, where's a good one? Let me go back to this one. So let's say if I think what you're asking, now that I think about it more, is basically what if we make the red region stiffer than the orange region, right? Yes, you can do that pretty easily. You just assign a different property to these red particles versus the orange particles. So yeah, there would be, you're not really getting okay, good. Yep, yeah, that's not hard at all. You just give a different property to those. Okay, when running, let's see here, Pete, when running 100 radios models, what HPC configuration was used? For this specific model, I think I can check actually. On this specific model, it's actually pretty basic. I believe I ran it on 64 cores and then I think it took, let me check. I believe it took like 4 hours. Like, wasn't that bad. But again, that's because we only ran it for I think like 30 milliseconds or something. But give me one moment. I'll check right now. Sales tickets. Let's see. Okay, I'm checking now. Yep, we used 64 cores, and it took about 2 hours. This model took 2 hours to run on 64 cores, and we ran it for. Let me double check. Input. And we ran it for only 5 milliseconds. That's why it was just a 5 millisecond impact, and that's why it was it went so fast. So I'm gonna just let's see if I can reply to, let's see, when running, I'm gonna answer this 5 millisecond simulation using 64 cores. Ran for 2 hours in real. Okay. All right, there's that. Okay, from Anor. Is there an alternative to Radios in the HyperWorks suite? I don't see it in my HyperWorks software. For this type of simulation in the HyperWorks suite, I believe only radios can do this kind of high velocity impact with SPH elements. I think Radios is the only one in the HyperWorks suite. Or both Siemens and Altair. Okay, from Pete, okay, I already answered that one. Okay. All right, I think I answered everyone's questions. If I didn't, if I missed someone's question, please put another message in the chat and remind me. Okay, from Jim again. Do you know any examples of FAA accepting an analysis with SPH elements for airworthiness? I'm not sure. No, I don't have any examples of that. I would doubt that the FAA would, I think you mean in lieu of physical testing. I come from the automotive background, and at least the in the automotive world, simulation is good, but all that the NHTSA and IIHS care about is the physical test. So I assume the FAA would be similar, where they the simulation is for the development, but you still, in order to pass something, you still need to use the physical test. But yeah, I'm not sure. I don't know for sure. It looks like other people know better than me. Okay, if people still have questions, I can stay around. I can stick around for another couple minutes. Okay, let's see here from Jim again. What's the best way to jump in using the SPH? Yes, there is a tutorial. I'll put it in the chat now. We have radios for FSI, it's called, which stands for Fluid Structure Interaction. Let me see if I can find a link to it on the training, in the training hub. Let's see here. Learn. Okay, radios FSI. Sorry. Yeah, I know we have a course. I'm not sure if it's posted still. Simulation. Oh yeah, good question. I see another. So Jim, I'm still looking for the tutorial. I'll link it to you in a minute. I see another question from Eric. How long did it take to train the ROM AI? So let me go back to, let's say, is there a substantial amount of time? Oh, it's so much faster. It's way faster. I don't think, so again, the training was done by my colleague. I don't think it required, because ROM AI, it just looks at inputs and outputs. There's not a whole lot going on computationally. So let me go back to this. I think this is this is the slide. So effectively what this is, to generate each point on this chart here, let me pull this up like this. So to excuse me, to generate each point in this chart takes about, I think he said, like 1 to 2 minutes. So we had 42 combinations of hyperparameters. And then, so basically this is the training of the model, or I'm sorry. Each combination of hyperparameters took about 5 minutes to train. That runs through the whole 100 epochs, or 100 iterations. And then within each combination of hyperparameters varies the number of networks layers and number of neurons per layer. And but each iteration of that took about 5 minutes, and that gets you. And then finally, we found the most accurate model was the 3 layers of 80 neurons. But getting to that point took about 2 hours. It was like something like 5 minutes times 42 combinations, something like maybe 2 hours, 10 minutes, or something like that. But yeah, not long at all. And once the model is, well, relatively speaking, not that long. And once the model is trained, then you get results, in a couple seconds. So, and I believe this is just done on a normal laptop. I don't think the training takes much computationally. Okay, good. Okay, now I'll go back to Jim's question. Okay, can ROM AI models be extracted? That's a good question. I actually am not sure. I am not sure, but I can what you can do is you can contact the Altair or Siemens support and ask them that question. Someone with a more ROM AI experience can maybe answer that better. Yeah, I I don't I think no, because where's the ROM AI? I believe we called it kind of a black box. This little box in the middle. I think it's a black box where you can't see that, but maybe there's a way to extract it. I'm not sure. So yeah, maybe just ask Altair / Siemens support. Depending what country you're in, Altair might still exist. In the US where I am, Altair is no more. Okay, and Jim, I'm still looking for the latest training for SPH elements. AC. SI. Okay, here it is. There's one in March, and I think, yeah, okay, I'll just see if I can link this. Yeah, there's a virtual training in March. I don't know if we have any e-learning for it, but I'll check as well. Okay, give me one sec. I'll pull up the chat again. Okay, Jim. There. Okay, that is, I just linked the virtual instructor-led training. And let me see if there's some e-learning as well. I think. I don't think we have FSI e-learning yet. No, we do not. Yep, so that's unfortunately you will have to wait until March, but yeah, in the meantime, if you go, I think there might be some things on YouTube as well. Yeah, you can check that out. And again, if you're interested, you can create another support ticket again on Siemens or Altair, and then just ask for intro to FSI or SPH, and then we can have one of our experts help you out with that. Okay. Okay. I'll give them, because you guys are asking good questions, I'll give you one more minute. And if nothing else comes in, we'll close the meeting. These slides, I think, yeah, I can should probably post this somewhere. They're not publicly available yet. Maybe I can. I wonder. Yeah, I'm not sure if they're posted anywhere yet. And I need to find out if I can share them. I'm not sure. But for now, no, I'm not sharing the slides. Okay, well, I don't see any other questions coming in, so we'll go ahead and end the call. Thank you everyone for being engaged and paying attention. And again, if you have any other questions, please go ahead and reach out to the Altair community or the Altair support or Siemens support, and we can have one of the relevant expert help you out. So thank you very much. Have a good rest of your day.